So far in this set of videos, we've learned all about momentum. We've learned about impulse and how impulse and momentum combine. We've talked about the impulse momentum theorem. We've looked at all that. And now I want to look at this concept that you may have heard of before called conservation of momentum. All right. In this whole section, we're talking about a lot of collisions. Conservation of momentum and momentum isn't only about collisions, but we can use collisions to, that's probably the most easiest way to illustrate it, I guess I could say. All right, so if we want to talk about collisions, I want to actually just do a pretty simple collision with you. So this is a, hey everybody. What I have here is a ruler, pretty simple. I've got a quarter. You can see it closely. Normal quarter. There he is. Old George. It's kind of hard working when you have to look at the screen and the camera at the same time. And there's a dime, right? So I have a ruler and a quarter and a dime. What I'm going to do is simply place the ruler. I need another ruler though, because this one isn't quite so good as this one. There we go, because now the whole thing is flat on the table. Dime is over here. I'm going to take the quarter and simply shove it toward this end of the ruler, right? And you can probably predict what's going to happen. The dime will move this way. Okay, so watch, here we go. And actually, you didn't see it, but the dime moved off the end of the table. Maybe I can move the camera back just a little bit so we can see the whole thing. There's the end of the table. Here we go, one more time. Quarter coming, dime will fly off the end. There it goes. Okay, so I had to catch the dime in my hand. Now the question is, what's going to happen with if I do this the other way? Obviously, the momentum from the quarter was transferred to the dime at the end of the ruler, and it was transferred through the ruler. The ruler didn't even necessarily have to move. Momentum is still transferred if we switch it the other way around. Okay, so now I have the quarter at rest at this end, and I'm going to shove the dime toward the ruler. You can make your prediction about what's going to happen. Hopefully you can predict that the quarter will move, but let's see what actually happens. The quarter moved, but it's still on the table, just barely. I threw the dime actually quite a bit harder than I did the quarter. Okay, the momentum was still transferred, the dime still moved, but you can see the dime didn't move near as much, and the question is why? Well, it's easy to see when we compare the momentum of these two objects when they're moving at the same speed. Since momentum takes into account mass and speed, if we take speed out of the equation because they're both going the same speed, theoretically, then obviously the one with more mass has greater momentum. And so when we transfer the momentum of the quarter to the dime flies off the table fairly easily. But when it's the dime doing the colliding, the dime doesn't have very much momentum, and it gets transferred to the quarter. The momentum is still the same in both cases. Whether you're talking about the dime or the quarter, the momentum of the dime equals the momentum of the quarter. But because the quarter has much less mass, the velocity has to decrease in order to equal the momentum, the smaller momentum that the dime has. And vice versa, since we had a high momentum from the quarter, and the dime has much less mass, in order to get the same momentum, you have to have a higher velocity from the quarter. In other words, the quarter actually came off the end of the ruler faster than, or the dime came off the end of the ruler faster than the quarter hit it from the other end. Simple but interesting illustration to start us on our notes. Okay, so let's look at the notes now. Whenever two objects collide, the momentum lost by one object is gained by the other object. All right, so that's easy to see in the quarter and the dime. Okay, the momentum lost by the quarter when it hit the ruler and stopped was gained by the dime, and vice versa. But in all situations, all collisions, the law of conservation of momentum says that the total momentum of the system cannot change. Whatever the total momentum of the quarter and the dime was before the collision, it's the same momentum that they had after the collision. In other words, rho before equals rho after. Remember, rho stands for collision. Okay, so let's talk about collisions. There's three specific type of collisions that we're going to talk about in this class. Okay, again, conservation of momentum doesn't always have to do with collisions, but in this class, the most common examples of the conservation of momentum will be collisions. We have a bouncing collision where two objects come together, bounce off of each other, and move apart separately. The second type of collision we'll talk about is a locking collision, where two objects collide and actually physically stick together in the collision, and they move off of the collision as one object. And then the third type of collision is called an explosion, which I'll talk about exactly what that means in a minute. So, bouncing collision, let's talk about it. Imagine that you have two pool balls, okay, two billiard balls. This is a cue ball, and it's moving toward the 8 ball, which is initially at rest. Okay, this is what's happening before the collision. All right, and we have all this information about these two balls. We have their masses, we have the velocity of both of them as well. Okay, and then we're given this picture for after the collision, and you can imagine if you've ever shot a cue ball, if you've ever played pool, you know that afterward it's possible, though it doesn't always happen, it's possible for the cue ball to keep moving in the same direction, although the velocity decreases. Compare these two. And then afterward, obviously, the 8 ball will be moving because the collision from the cue ball caused it to start moving, and so it begins to move in the same direction. It won't always happen this way. Sometimes the cue ball stops depending on how you hit it, but let's picture that this is what's happening. All right, I'm going to go through and basically fill in all of this information. This is the first way that I'm going to show you how to work these problems. This is, I guess you can call this the table method, okay? It's not as much algebra. You're doing the same thing if you do the algebra method, which I'll show you a little bit later, but this makes more sense to some people because it's more pictorial, okay? So let's look at what we can find here. We know the mass and the velocity of this ball. And if momentum is mass times velocity, then I can very easily find the momentum to begin with of the cue ball. And that is 0.25, and the units would be kilograms, meters per second. But I'm not very concerned about the units in this point. I just want to get the numbers. Likewise, I can find the momentum of the 8 ball, and since it has a velocity of 0, it also has a momentum of 0. And then the total momentum of the system is simply the momentum of the two objects combined, and that's 0.25 plus 0, which gives us a total momentum of 0.25 kilogram meters per second. Pretty simple, right? And now that we know everything we need to know about the initial stage, I now know that since the momentum before the collision has to equal the momentum after the collision, then I can take this number and bring it right over here and put it in for the total momentum after the collision, because that's what the law of conservation of momentum says, that the total momentum before and after the collision must be the same. So we have the collision that happens here, the total momentum changes. The total momentum doesn't change, even though a lot of other things may change. Well, I guess the momenta and the velocities of the two balls. The mass will not change. Okay, the mass of these things, at least in this course, is not going to change. So the masses still stay the same. I don't know the velocity of this ball, so I can't calculate anything here yet. But I can now calculate the final momentum of the cue ball because I'm given the final velocity of the cue ball. And half of 0.4 gives me a momentum, mass times velocity, of 0.2. And now we can reason that if the total momentum of these two added together is 0.25, and we know the momentum of the cue ball is 0.2, that means there's only 0.05 kilogram meters per second left for the momentum of the 8 ball. Okay, and this may not be an entirely realistic situation, but let's just imagine that this is what happens. The momentum of the 8 ball has to be 0.05, because 0.05 plus 0.2 equals 0.25, and that's what these two have to add to. All right, and lastly, because I know the momentum of the 8 ball, and momentum equals mass times velocity, rho equals mv, I can now say that 0.05 rho equals the mass, 0.25, times the velocity, and simply solve for velocity by dividing by 0.25 on both sides. And that means that we come out with a velocity of 0.2. Velocity of 0.2. So that's how we got all those numbers. And that's how the law of conservation of momentum works. That's how we can use the law of conservation of momentum to find all this information that we need. Ultimately, at the end of this whole section, and you might want to write this note out here to the side of your notes, the most important thing to consider in all of these collisions is how many objects are there. And perhaps instead of how many objects, I should say how many separate objects. How many separate objects are there at any one point in time in these collisions? And it's important to realize that before the collision we have two separate objects, and with a bouncing collision we also have two separate objects after the collision. And that's important to know, because if you're solving this algebraically, then each separate object must get its own row. It must get its own momentum. So to write that algebraically, I can say that the initial momentum of object number 1 added to the initial momentum of object number 2 must equal the final momentum of object number 1 added to the final momentum of object number 2. Algebraically, that's what it would be. And then you could flesh that out further and say mv, mass times velocity, and we'll do that in just a minute. But basically, that's what it means. In other words, each separate object has its own row, has its own separate mass times velocity. Let's do the locking collision, then I'll be done with this section of the video. Locking collision. You have two objects, again, moving towards each other. They could both be moving. One of them could be at rest, as in this case. But the point with a locking collision is that for some reason, maybe there's some sticky tack on the end of this cart, they now stick together and move off of the collision as one object. And that'll change one very important thing. So let's start at the beginning, or maybe we should start like this. We should note that there are two separate objects before the collision, and there's only one object after the collision. Important to know. Momentum. We have the mass and the velocity of the first cart, the white cart, and 3 times 2.2 gives us a momentum of 6.6. And again, since the second cart is at rest, the velocity is 0. That means it has 0 momentum. So the total momentum of the system before the collision, 6.6 plus 0, is 6.6. And once again, the law of conservation of momentum says that that can go over here to the total momentum, because the total momentum has to stay the same. 6.6, 6.6. And now it's really beautiful, because since we only have one object over here, this total momentum must equal the momentum of this one object. There isn't any other object to take up any other part of that momentum. So I know the momentum of this object is 6.6 because the total momentum before and after the collision is 6.6. Okay, I have blanks where the mass and the velocity is, and there's one of these that I can get real easy, because I know that this two-cart system now, this two carts stuck together, has the mass of the first two added together, and 3 plus 3 equals 6 kilograms. And now that I know the mass, it's really easy to solve for the velocity, because rho equals mv. 6.6 is the rho. I want the mass, and the mass is 6, and I want the velocity. Divide by 6 on both sides, and you get a velocity of 1.1 meters per second, and that'll go in right there. So I've now found that in this particular collision with these particular carts, these two carts will move off to the right at a velocity of 1.1 meters per second, according to the law of conservation momentum. Algebraically, what this is with a locking collision, once again, we have two objects before the collision. Those two objects get a separate row, so I can say that rho 1 initial plus rho 2 initial equals, now we don't have two objects, we just have one, so I'll call that rho total final. Algebraically, that's what that means. Once again, rho equals mv. Every time you see a rho, you can flesh it out and put a mass times a velocity for that appropriate circumstance at that point. Bouncing collision, locking collision. I'll do another one of those problems in just a moment.